In this presentation on pneumatic control system, we shall be discussing about the components and their function, circuit diagram, system symbols, filter and lubricator, I-to-P converter, solenoid valve, 2x2 and 3x2 valve, pneumatic cylinders, control valves, direct and reverse acting valves, valve positioner and fail-safe position of a valve. Let us see how a pneumatic system works. Pneumatics is the science and technology of pressurized air using piped compressed air or a similar gas such as nitrogen to transmit force and energy. Pneumatic machines need 5 basic components to make, store, control and use compressed air. Now, let us see the purpose of different components. A compressor makes the air, produces the air. A reservoir or receiver stores the compressed air, and then one or more control valves are there to control the movement of the air. A circuit that moves air between the system components. An actuator or motor uses air to do something, that is valve or position in cylinder. Now let us talk about the main components. Main components of the compressed air production, transportation and distribution system consist of a compressed air to compress air, air dryer to remove moisture from air, dew point of air, it should be less than minus 40 degree centigrade. A storage tank to store compressed air, pressure gauge to indicate the pressure, automatic drain to remove the condensate from the air, filters to remove the dust from the air, and air lubricators and pipelines. Air consuming system components contains inlet air filter to remove the dust, air takeoff valve for isolation, auto condensate drain that we call trap also, air service unit, it is lubricator, I-to-P converter, directional valves to change the actuator directions, actuators, they are mostly cylinders, different type of valves, dampers, guide vanes and speed controllers. Now, in this diagram, let us see the main components of a pneumatic system. So, you see the air comes to the compressor through a filter and the air get compressed, then it passes through a cooler where it is cooled, and after that the moisture separator removes the water from the air and it goes to a receiver where the air is stored at a pressure, and then there is a system to control the pressure of the receiver, which controls some pressure switches and motor control system. After that, air goes for secondary treatment. Secondary treatment means the air is dried mostly through the silica gel or molecular sieve, and after that the air goes to the control valve, which can change the direction of the valve in the required direction to move the piston inside the cylinder, which is actuator. Now let us see a complete system in the diagram. On the top the diagram is shown, and the part, if you see on the bottom, all the it is shown as the symbols. So air is coming from the air going to the compressor, then it is passing through the cooler, that is chiller, then the air is separated, it goes to the refrigerator tank. From there it goes to the air humidifier to remove the moisture from the air and to get a dew point less than minus 40 degrees centigrade. Then this is called FLR, filter regulator unit, where there is a filter, there is a regulator to control the flow, and then there is a lubricator to lubricate the air, and after that the air passes through to the cylinder depending on the direction required. So this right from FLR up to the cylinder we call is a general basic circuit. Now let us see the symbols for that. You see, this air compressor is shown like this triangle. This is the symbol for filter. This is the symbol for moisture separator or trap. This is the symbol for tank. Again, there is a air dehumidifier. This is the symbol for that. And for air quality control, this is symbol for filter. This is for regulator, which regulates the oil pressure. And this symbol is for lubricator. Here, this is the symbol for the control device, and this is symbol for the cylinder. So let us see how the air filter and water trap works. Air filter and water trap is used basically to prevent any solid contaminants from entering into the system. Condensate, it removes the condensate water vapor and present in the compressed air. So let us see the construction. This is air separator, and here air enters from left hand side and it goes down these cones here. This is the cone to direct the air comes here and goes down and takes the U-turn and comes up. Now when it comes here, the baffle, it hits the baffle and the water gets down. Again, there is a deflector cone which is used to any water going up through this deflector cone will go down. This is the filter. So the again air is passing through the filter and from right hand side it goes out. Now here through a video, let us see through the video, let us see the air separation unit.
As you can see, this is a lubricator which is full of water. It's connected with two separate lines, one for air with water and the other for compressed air. But before I proceed, let me make this very clear that this presentation is a demo presentation only. Hydrant moisture separator incorporates two types of separating tools. The first of which is the baffle type. When the air strikes against the reinforced steel baffle provided within the separator on the inlet, there is a further compression at the point of strike. Any water in liquid or fog form will be initially separated at this stage itself before it has a chance to enter the inlet of the separator. This greatly increases the life of the collaser while performing as a separator itself. After the air has been relieved of some of its separator by the baffle, it is subject to another relieving mechanism, the collaser. See, this is how this collaser operates. The moisture has a tendency to be attracted to the solid stainless steel due to cohesive forces. Any gathering of water will form or drop, which increases in size and eventually becomes heavy enough to drop downwards to be collected and disposed of. Now, fresh air is there in the outlet.
Now, let us see how a lubricator and functions. So on the left hand side, we see the diagram of a lubricator. So why we are using lubricator? Many pneumatic system components, all pneumatic tools perform better when lubricated with the oil. So injecting an oil mist into the air stream which powers them can continuously lubricate the valve, cylinders and air motor for proper operating and long service line. So let us see how it works. You see, this is oil enters from here. Oil enters from here, and we through this knob we can adjust the feed of the oil. Then the oil comes, and it through this capillary the oil comes down, and then it takes a turn, U-turn, and goes up, and from here it goes out. There is a venturi for drawing the air. On the right hand side, we are able to see a moisture separator which is already explained in the previous video. So air is coming from here, it is moving like this, going down, again it is going up, and moisture gets separated here due to the change in the direction, and then the air goes out. Now, solenoid valve is a very important component in this system. A solenoid valve is an electromechanical control valve. The valve features a solenoid which is an electrical coil with a movable ferromagnetic core in its center. The core is called plunger. In the rest position, just closure of a small orifice. An electric current through the coil creates a magnetic field. The magnetic field exerts the magnetic force on the plunger. So let us see in the drawing here. You see, this is the solenoid valve. Here this is the solenoid coil. This is the stem of the valve which moves up and down. So from here the air or whatever is there, it comes from here and then goes out from here. But when we move you see, when we are moving it, energizing it, energized, and is open this port, and then the air goes out. Now, another very important component in the system is I to P converter, that is current to pneumatic air compressor. So what happens? As soon as the coil in this is, it has got a magnetic coil, it has got a armature, this is a shading ring, you can see the spring, and this is the valve seat. So a spring is pushing the valve seat, and so as soon as the coil is energized, a magnetic field is created which pulls the plunger up toward the center of the coil. This opens the orifice. So this orifice, you see on the right hand side, this orifice opens, and through this the air or whatever media is can pass. This is called normally closed or NC valve. In normally open or NO valve, its work in the opposite direction. It has got different constructions so that the orifice is open when solenoid is powered, and when the solenoid valve is actuated, the orifice will be closed. By varying the current to the coil opening and closing of the orifice can be carried out, which will vary airflow to the actuator. In the current to pressure IP converter, we usually give input a signal of 4 to 20 milliamps. If the current signal is high, then the power of the magnet will increase. then the flapper will move closer to the nozzle, so the less pressure will escape through the nozzle outlet. In this way, the outlet pressure can be proportional to the input current. For input current 4 to 20 milliamps, you can get output pressure of 3 to 15 psi. So let us see the same thing in a diagram. You see, from here a 20 psi air is coming, it passing through this air, and then it is coming here in this pipe. The pipe is coming here. There is a nozzle, and there is a, this is the flapper, this is flapper, and there is a gap here. Now what, this is a spring, and here this is the magnet. So what happens when when there is no current, the spring will pull it up, air will get more and air will get out or drained through the gap between the nozzle and the flapper, and accordingly then you will get a very less pressure, as low as up to 3 psi. When it is when it is actuated, then this magnet will pull the flapper down, this gap will start closing, and we can get a pressure up to 15 psi at the outlet. So let us see the same thing through a video. So let us see here what is an I to P converter.
The letters I and P represent signal types. I represents an electrical current signal, whereas P represents a pneumatic or pressure signal. The I to P transducer is a common conversion device that allows an electronic signal to be converted to a pneumatic signal. I to P transducers are commonly required in process control applications using pneumatic control valve assemblies. Controllers like programmable logic controls, PLCs, or distributive control systems, DCSs, use an electronic output for control, such as a 4 to 20 milliamp signal. These electronic signals are not compatible with pneumatic actuators. If you want the control valve to respond to the electronic control signal, the signal must be converted to a pneumatic signal. That's where the I to P transducer comes in handy. I to Ps are available for several different electronic input signals. They may also be configured for different pneumatic output signals as well. So now let's take a look at how an I to P operates. In this animation, we have a 4 to 20 milliamp control signal that needs to be converted to a pneumatic output signal. A common pneumatic output signal is 3 to 15 psig. The electronic 4 to 20 milliamp input signal is applied to an electromagnet. As current is changed to the electromagnet, magnetism increases or decreases. This change in magnetism affects the position of a beam. If magnetism is increased, the beam moves toward the magnet, and as magnetism is decreased, it moves away. On the opposite end of the beam is a nozzle and flapper assembly. The movement of the beam positions the flapper in relationship to the nozzle to create changes in nozzle pressure. An increase in magnetism in this example moves the beam closer to the magnet, which moves the flapper closer to the nozzle, and we'll see the output pressure increase from 3 to 15 psig as the input current is adjusted from 4 to 20 milliamps. So the output is directly proportional to the input. I to P transducers can be used as standalone devices operating the control valve directly.
Now we will be looking the different type of the valves. So you see there are 2 by 2-way valve, that is called two-port valves. It has got an inlet port. It has got an inlet port. This is 2 by 10 with inlet port, and then there is a outlet port. The left hand side shows the normally open valve. It means that when it is energized, the valve will close. This is normally closed valve. Normally closed valve in the energized state. In the energized state, you see what is happening. In the energized state, the air will pass through it, and in the de-energized state, when this moves on this side, the air will stop. This is the 3 by 2-way valve. 3 by 2-way valve have 3 ports and 2 positions and can therefore switch between the 2 circuits. 3 by 2-way valve can have different functions such as normally closed, normally open, diverting, or universal. More ports of combination of the valve in a single construction are possible. Now let us see in a 3-way by 2-way valve. You see what is happening is that these are 2 ways, but you can direct the valve. When you can move it, and you can pass the air either from this side or from this side. So we will be able to seeing it here 3 by 2 valve in a bit more detail. You see here in this case, this is the normally closed position. Normally closed position means because it has got 2 positions, 3 connection ports. So this valve can be closed for multiple applications such as switching between 2 circuits or actuating on a hydraulic cylinder. So here you see these are the 2 points. Now this is a normally when the valve is closed. When the valve is closed, one opening is here, another opening is here, and so the air is not passing through it. This is normally open. In normally open, you see either this will be the position, this will be the position, or it will be decide. When this arrow comes, there will be a cross flow. Then when this arrow comes in position, there will be a straight flow, and this one is used for the diverting. So by whatever is coming, you can divert either to the left side or right side, and this is the universal valve which can be used for any type of operation. Now here we are able to see the different working of the different type of cylinders. So here on top we are able to see a spring loaded cylinder. So see when a spring is pushing the piston in cylinder to the left hand side, and when the air is coming up, it is moving towards right side. Now here we will be able to see how this 2 by 3-way valve operates and how it changes the position. You see the air is coming from the here. In this position is going from here. In this position air is going from here, pushing it to the right hand side. And then it is changing and air is going from here and pushing the piston to the left hand side. Here also we can see the same thing. You see what is happening, that when a spring is pushing this up, air is coming from here. Now it is happening, air is coming from here. When air comes from here, it will push it on right side. When air goes from this side, now air will go push on the left hand side. Same thing on the right side, you are able to see how it is happening in a control valve, and this is the single axis. So you see 4 to 20 milliamp signal is coming and it is going to I to P converter, and when the orifice is closed, it is 3 psi. In 3 psi the valve is opening, and in 15 psi full air flow the valve is closing. This bottom one is showing how the valve opens and closes, and then when the valve is closed, there is no flow. When the valve opens, the flow takes place. Here we will be able to see the direct and reverse acting control valve. Direct acting control valve is a valve which is used when the air closes the valve. It means the spring opens the valve. So this is your air to close or direct acting valve. So when the air comes, you see air comes from here. When air comes from here, from the top, air will press the spring and the valve will close. In present situation, you see the valve is open by the spring. In the reverse acting, air is supplied from the bottom. So spring will close the valve. This is showing in the closed position. And when air goes from the bottom against the spring compression, it will press this disc and the valve will go up and the flow will takes place. Say here, you see, we can see it here. This is a air to close valve. This is a air to close valve, and this is air to open valve. So you can see on the top one, when the valve is going up, air is opening, air is going from bottom, air is opening, and the flow is taking place. While in this diagram, if you see that when the air is going to 15 psi, it is closing the valve. So it is air to close or direct acting type of valve. Now let us talk about the fail-safe status of a valve. Fail-safe of a status of a valve is decided on the process conditions that when the valve should operate when there is a loss of power or signal. So the valve safe position is a safety precaution that protects your process in emergency situation. There are a few different fail-safe scenarios, each having its own consequences and safety effects. It is important to remember that valves are generally pneumatic, meaning that air function is based on the air pressure. Air has to be added in order to open or close the valve depending upon how it is set up. If you lose power or air pressure, how you want your valve to react. Your decision is dictated solely by your process. Every process is unique, so you need to analyze your process and consider consequences of the downstream. Now, let us talk about fail to open, air to close. Fail to open means a valve solenoid will open at the loss of signal or power. This type of valves require air pressure to stay closed. Once the required air pressure is gone, the valve will naturally open. Under a power outage, the source of air or pressure would be lost and the valve will fail open. If the solenoid operated valve, the solenoid will be off and the valve will open. Now let us see the fail close or FC position. Fail close means that the valve will close when signal is interrupted or lost. This is the opposite scenario of the air. Since air pressure is needed to keep the valve open, it will automatically close when the power is lost because there would be no longer a functioning air source. If solenoid is operated, solenoid will be off, or solenoid bulbs, then the air will open. Now, you see here, this is the fail to open. This is the fail to open. So, air is closing the valve. If the air fails, the valve will open, and this is fail to close. So, air here, it is reverse. Now, let us talk about a control valve positioner. So, you see, this is the positioner in the control valve. Here, this is the feedback linkage, this is the air supply, and this is the position of the control valve. positioner is a motion control device designed to actively compare a stem position against the control system, adjusting the pressure to the actuator diaphragm or piston until the correct stem position is reached. So, here in this we will see different components of a valve with positioner. So you see this is the valve body, this is the valve body, and then this is the actuator assembly here. This is the diaphragm which operates the valve, and then these are the springs. This is the valve stem. This is F is the position indicator, valve position indicator, and this is your valve positioner. This is your valve positioner, and here the air connection is from the diaphragm in this particular valve. Now we will be going to see a video which will tell us what's a positioner.
Pneumatic actuators are commonly operated by air signals that come from a controller. In some cases, the controller signal alone isn't enough to overcome forces on the actuator, such as friction in the actuator or the valve stem, or fluid pressure acting against the valve disc. To overcome these forces, some actuators must be provided with a different supply of air that's capable of applying higher pressures than the air signals from the controller. This is accomplished by using a positioner along with the actuator. Basically, a positioner is a device that uses a separate supply of air to ensure that an actuator correctly positions a valve in response to a change in the air signal from a controller. In other words, a positioner's job is to place the control valve in the position called for by the controller. The positioner shown here has 3 gauges. One gauge indicates the supply air pressure to the positioner, and another indicates the output air pressure to the actuator. The third gauge indicates the input signal pressure from the controller. A mechanical linkage joins the actuator stem to the positioner. This mechanical linkage may also be called a feedback linkage. As the actuator stem moves up or down, it also moves the linkage. The position of the linkage indicates to the positioner when enough movement has occurred to correspond with the air signal from the controller. When a positioner is used with an actuator, the signal from the controller goes to the positioner instead of directly to the actuator. The positioner controls a source of air that enters here and is sent to the actuator through this line. When the controller sends a signal to close the valve, the positioner receives the signal and converts it to the appropriate air pressure using this air supply. This pressure is then applied to the actuator to close the valve. The feedback linkage indicates to the positioner how far the valve is from the desired position, in this case, fully closed. As the valve moves toward the fully closed position, the feedback linkage causes the positioner to change the air signal to the actuator, so that as the valve reaches the fully closed position, actuator movement is stopped. On a piping system diagram, a positioner may be represented by this symbol.
Now let us talk about the open loop and closed loop system. So first, in open loop system, the output does not affect the controller action of the system. In other words, the system whose working depends on time is known as open loop control system, and it is free from any feedback. So the input is coming to the controller is processing, and it is going to the output. There is no feedback. Now, in closed loop control system means that the output of the system depend on their input. The system has one or more feedback loops between its output and input, designed in such a way that they automatically provide the desired output by comparing with the actual output. Generates the error signal, which is the difference between the input and output. So you see, this is the reference, this is here the input, this is the reference, and through amplifier controller it is going to the process, the valve is operating, and the actual feedback is coming, which is telling that how much is the error, and correction takes place automatically. So thank you very much for your patient listening and viewing. Now, please press like and subscribe my channel to get information about the new videos being uploaded in the future. The next video which will be uploaded is on hydraulic control system. To get a free more than 100 slide PDF of this system, please send a email to me. Thank you very much.